Hi, good evening and welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really just answering technical questions that have come in during the week. I know I always say this, but today I've got this dated the 29th of December 2024, even though in fact we've gone live on the 28th of December 2024. So my apologies for that slight discrepancy in the date. With that said, let me just go forward anyway with the webinar. If there's anything that catches your eye, I mean, I will link back to some things on the web store. The discount code for the web store this month is here. So if you put that, hopefully I'll remember to put it underneath the video as well, and you can use that. With that said, let me go forward a little bit more now, and just say that the questions I'm going to answer tonight are, I had an email come in, which is really a correspondence, but just know that anything technical, or we like to answer it in these webinars, and we always kind of anonymize, the answers, etc. So I am going to talk to you about the analysis of lead tonight. I'm actually going to contrast a technique that I've not heard of. I do understand it now, but I hadn't heard of it, called Agnes, and the acronym slips me for a second, but it's like, I want to say sort of gradientless Nernstian deposition detection of lead, but it's not for lead. They were doing it for zinc. But anyway, let me talk about Agnes versus ASC, anodic stripping voltammetry. I'll also talk about transdermal biosensors. I do find it amazing that people still ask us whether we do transdermal systems, so I'll definitely prove that we definitely do. Let's say it's also going to be quite a little bit relevant to actually question number one, because in question number two you will see these biosensors. When I hope I can hold up a couple of examples of biosensors to the video now. So here's a couple of examples of biosensors. These will be, in fact, those two are the same. These will be featured in the webinar this evening. But I'll also be showing a very different type of biosensors as well, a transdermal one shortly. I'll also talk about embedded sensors. So that'll be something where somebody wants to know, can we do these kind of things on flexible sensors, flexible electronics? Quick answer is yes. Miniaturization of circuits. We've got them miniaturized to a certain degree. We just haven't, the application they have is quite demanding. It's very small. We haven't miniaturized to that scale. Is it possible? Yeah, it absolutely is possible. But the more you miniaturize electronics, and if you want to embed them in somebody's body, it just becomes a very demanding, let's say, application, but it is possible. At ZP we are doing embedded sensors. In fact, I've just taken an image out, but I've got some images that I'll put on later on for embedded sensors. And closed loop, I've taken out what they're trying to close loop on. But closed loop can sometimes mean that you have a sensor and you may have an actuator. In this case, the actuator may be a pump, and you're pumping something in depending on what the sensor is actually saying. So they're doing this kind of closed loop delivery in diabetes a lot. I say a lot, and I kind of realize I have to kind of be a little bit careful with that statement. They're starting to do it on diabetes, where you have a CGM, a continuous glucose monitor, and they're constantly monitoring interstitial glucose, and then they're pumping insulin or doing cessation on insulin based on the glucose reading. Skin patches for electronics, I'll also try and get some images for that as well. So that said, question number one. So at Zimmer Peacock, I've got the FoodSense, no, in fact, I've got the Sensi All platform in front of me. So, I mean, this is a really, I want to say a really unique type of potentiostat. So this is a potentiostat that can do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cycle voltammetry, square wave voltammetry. But it's a very different type of instrument, because not only will it take these kind of electrodes, which will just kind of click in, so there's nothing like that. We can also then turn it into actual assays. So I'm just going to grab the app, in fact. So I've got the app installed on my phone. At the moment it says lead sensor. So I've actually got it, so there's different QR codes here. I'll just scan another QR code just really quickly. I've just put it into caffeine sensor mode. I'll do another one here, which is nitrate. I missed it. But we have all these different, let's say, modes that we can run off this particular potentiostat. So with that said, let me go to screen 2. So we do have a lead sensing mode, and we can therefore measure the lead in water like saline or like a salty solution or even fresh water. There is a video online. I'll try to remember to put a link to this video after this video has actually gone live. But the reason I bring it up slightly is because you can see this kind of lead system in action, and I will answer some questions that have come in about this lead system as I go forward now. Right, so you can see a video online, and I'll put a link to the video. So the questions that have come in, they're quite technical, but I'm happy to answer them. The question here is, what fraction of the sample lead is it measuring? All the free and labile species? So what we're measuring is total lead. The reason this has come up is because the person who's asking this question is familiar with a technique called Agnes, and I realise in Agnes, having read a little bit about it, I must admit I hadn't heard of it. It seems to, it sort of comes across as a kind of a subclass of anodic stripping voltammetry, but they use how do I put it? They use a potential for the deposition of lead, which is closer to the equilibrium potential, and because of that, I think they can argue that they get better speciation. Not all the lead will necessarily just deposit, and therefore they can kind of be a bit more specific in what they actually do deposit. Now, what we're doing on this particular system is putting enough potential, and we're what's called well away from the equilibrium potential. So in fact, we're doing total lead is the quick answer. Just trying to scan the QR code now for lead. There we are. Scan the QR code for lead. This will become a little bit clearer in a minute, but the way this system works is this is essentially the instrument or the potentiostat. If you're using it in R&D circumstances, you would think of it as a potentiostat. If you're actually using it for analyte analysis, then you would feel of it more like a sort of actual instrument. And I'm in lead mode at the moment. But their questions are quite specific. So the quick answer to your question is, because this person's familiar with Agnes, they're wondering if we're just doing particular fractions of the lead, but the answer is no, we're doing all of the lead because we're actually doing anodic stripping voltammetry. Are we acidifying? Yes, we are acidifying. In fact, if I just share my screen for a second, this is the lead app. If I just go continue, whoops a daisy. If I just go, what it will actually ask me to do is add one part of the sample to 4 parts of our buffer, and it's our buffer that acidifies it. I won't necessarily say what that pH that we take it to is, but you can probably guess what that pH, let's say, is. So the quick answer is yes, we are actually acidifying the sample. What is the typical cost of the gadget? So this Sense-It-All, which I have in front of me, it's either a potentiostat or it's actually a final instrument. It's a bit of an unusual instrument, let's say. So if you're an R&D scientist, it's unusual because you could do your fundamental science on it, but actually you can then actually use it as a, let's say, go-to-market instrument. So if you want to get those sensors out of the lab and into the field, you can actually do that as well. But the quick answer is to that question, it's actually 1,600 euros. It's probably worth knowing how powerful it is, because in fact, this is just, we use it for measuring the capsaicin in chili, the gingerol in ginger, pH, nitrates, total antioxidative capacity, glucose, potassium, testosterone, something called NADCC, which is basically free chlorine using water sterilization. That's correct. Just thinking aloud. And then lead and caffeine. So we use it a lot of things. You can imagine this, people talk about multi-analyte, and the quick answer is this really is a multi-analyte system. What is the cost of the samples and buffers at low volume? It basically works out about 397 euros. I should have put euros in per sample. I got a vortexer, admittedly, and we did in the video when we were making this lead vortex it. You do not need to use a vortex. So when you're mixing, let's say it was seawater or brackish water or fresh water, these are all liquid samples, so you don't need to vortex it. Which is otherwise, we would vortex things. I mean, I'll hold up an example here actually. This is a kind of a very slurry like sample where I'm actually trying to extract caffeine out of coffee. and here I would like to vortex it. But I also understand that in this application, you know, this is going to be done in a kind of near a production facility. So in fact, they will have a vortexer. But when you've got very liquidy samples, something more like this, you do not need to vortex that. You can just give that a quick shake. There we are. Yeah, a quick actual shake. You don't need to be vortexing that. The cartridges are single use. The problem with, not the problem, but once you put a sample on there, how you then convince yourself that it's clean for the next sample is a really hard sort of convincing to be done. So we don't reuse sensors. It's what material is the electrode made of? I'm not necessarily going to say, but I will say one thing. It's definitely not mercury. I put a sort of jokey statement to myself, is it even legal to use mercury? And I did actually look up the legalities on mercury, but the quick answer is we are not using mercury electrodes. It is possible to do other elements, so we're probably going to do copper next. We do have a client who now wants us to do copper, which would be quite nice because we should be able to do lead and copper in the same sample, essentially in parallel. You know, so that will be kind of exciting. We haven't done it yet. The reason we can do all of this, I'll just turn that off, is because I mean, it is a technique called anodic stripping photometry. The good bit of what we've done is actually the way we've really shrunk it down and made it smartphone enabled, and we can crunch all the data in the cloud, and we can save all the data up into the cloud as well. I'll probably do a demonstration later on, so probably worth watching that. But we should be able to do other ions as well. We're going to probably do copper next. What's the limit detection? So we can get down to about 5 ppb. I didn't turn that into actually nanomoles. I should be enough of a chemist to be able to do that, but I don't think I could do it off the top of my head. But I work in ppb sometimes because I find the water industry is parts per million, parts per billion, kind of even parts per trillion. They're very interested in PFAS at the moment. These forever chemicals, and those are actually could be in parts per trillion. But the quick answer is 5 ppb. Can it be used with fresh and saline water samples? Quick answer is yes, because of that very important step that we do where we take one part of the sample and put it with 4 parts of our buffer that we ship with the product. Then you can understand that 80% of that sample is actually dominated by what we put in it. So then, you know, whether it's got the salinity, the pH actually all comes essentially from us, because we're 80%, when I say us, our buffer. We can also do phosphorus as well using electrochemistry is the quick answer. We absolutely can. We actually do have a phosphorus sensor, or phosphate sensor. For me, I'm thinking phosphate. The only problem I've got with this is because it's using what's called an ion selective electrode. Ion selective electrodes have good sensitivity. That means that from sensor to sensor we'll have good sensitivity, but it's the offset that's variable. So I could see that if I wanted to do phosphate in the field, I'd have to do a 2-part measurement. First part is essentially a single point calibration on the sensor, and the second part is add the sample. So we haven't brought phosphate to the platform for that particular reason, because it feels a bit harder for the end user, if I can put it that way, but that's why we haven't actually brought it. And they're also very interested in whether we can do continuous monitoring. The thing is, we can actually do continuous monitoring of things like nitrate. In fact, we're doing a lot of work on nitrate. It's a large program internally. We're doing it first of all for agriculture. It's not something I'm going to start releasing to organizations soon, anytime soon, but it's certainly something that's in development, but I'm not going to release it. But the quick answer is yes. You know, if you want to do continuous monitoring of nitrate, phosphate, potassium, electrochemistry is a good technique for this. The reason I'm kind of a bit hesitant was it because in life you can do discrete monitoring. So when I say discrete monitoring, I mean something like this system. You have a sensor, you come up, in fact I'll put this sensor on there. You have a sensor, you put a sample onto that sensor. I'll do a demo of that shortly. You get a result, and that's it's a discrete one-off measurement. Continuous monitoring, you'll see some images of us putting sensors into people shortly, and that's actually a continuous monitoring system. It's just always 10 times harder than trying to do a single measurement. You know, your sensor's got to be stable over time. You've got to have a whole system around it, so it's just harder. And I just you know, if just to manage people's expectations, it's 10 times harder to do continuous measurement than just to do a discrete one-off measurement. I mean, I made up the 10 times, but I'm just trying to say it isn't just a bit harder, it's a lot harder. So we do have a system for detecting lead in water. It's on our Sensi All platform. The reason that we have what these called these QR codes, so if I scan this QR code off my phone, which I will do, it puts my app now into lead mode, and now I can do a lead analysis. So my phone will now say lead sensor on it, so it changes my screen to here. When I press continue on the app will the app's in Bluetooth connection with the meter. The meter will make a analysis of that sample by electrochemistry. It will give the data back to the app. The app actually uploads it to a system called Julie. I'll just turn this off for a second. This is a real game changer because all the data is then put into the cloud and we process it and we basically send a result back to the smartphone, which is cool because then it means that somebody who just needs the result, let's say, can grab that result. It's also the cloud system also has an API built into it, an application program interface, which is useful because there's a lot of organizations these days that kind of want to map the results. But the fact that we're using a smartphone means that actually we've got essentially GPS on that. So we have time, date, who did it, GPS, and the result itself, and that can all be pulled across by API. So it's really good for sort of mapping onto a kind of Google Maps type thing as well. But anyway, you get a result on the phone, but we get all the results saved in the cloud, and that's really important for sort of traceability later on. So we are using anodic stripping voltammetry on that lead system. So I mean, anodic stripping voltammetry, I know I've forgotten what it's called. But anodic stripping voltammetry it requires this kind of pre-concentration. So we're depositing the lead on the surface. Then we oxidation. I keep saying lead, but it can be lead, zinc. It's lead at the moment. We're going to go to copper next, but don't feel like this is excluding other things like zinc. I want to say cadmium, arsenic, etc. When we concentrate it on the surface, then we actually oxidize it back. And when we oxidize it back off, we're often using voltammetry. The cartoon of it is we've got this electrode. And I say when we've got this electrode, I mean, I literally mean it's this electrode is what we are doing. So we have an electrode system that we are depositing the lead upon, no mercury involved. We deposit, that enriches the lead on the surface. We're not so species dependent. We're actually just measuring the total dissolved lead in that sample. And then we take that lead off by voltammetry. So the steps are deposition, and then so we have a deposition step where we deposit the lead down. Then we may have a rest time, and then we actually step the potential to an oxidation, and we basically strip it off, and we get a peak. The technique is a voltammetry technique. And it works pretty well. And basically the area under that curve is proportional then to how much lead is actually in that sample. And we turn that in real time into a concentration and send that back to people's smartphones. But we're not excluding them from having the raw data. Now, this person was kind enough to include some background for me. So I really had a look at this technique called Agnes as well. There we are. Absence of gradients and Nernstian equilibrium stripping. So I'm just going to say it again to myself so I remember. Absence of gradients and Nernstian equilibrium stripping. Okay, so I did take a look at a paper on this. The paper and the original authors are here. I can see that they actually invented this technique back in 1999, so kudos to them. If it has some elements of anodic stripping voltammetry in it, that you have a sort of deposition potential, and then you may have some a quantification potential. So that feels a bit like anodic stripping voltammetry, where we'll deposit and then we'll go to a higher potential where we can actually start stripping off or reoxidizing the, in our case it's lead. In this particular work I think these people are more interested in zinc often, but it has, so Agnes has some overlap with ASV, anodic stripping voltammetry. If you're not sure about voltammetry, I have a link here to a video on YouTube by yours truly. You can watch that if you're so interested. But that said, let me just jump in a little bit, and then I sort of finally figured out what, there's a few differences between Agnes and ASV. When we do anodic stripping voltammetry, this is the kind of deposition peak for lead. We will work at what I say at a potential that's far away from the equilibrium potential. So that means that any lead in there, boom, we're reducing it down. We don't care about the speciations, etc. We've kind of put enough energy into this system that any lead is coming down to that surface, and we're basically measuring the total. Now, one of the differences between ASV and Agnes is that they're a bit more subtle about that potential. So having read the article with here, this absence of gradients and inertia in equilibrium stripping, I can realize that one of the first things they have is this equation here, and I thought, oh, that equation looks a bit familiar. I mean, it was very familiar, really. I just didn't, first of all, I wasn't used to looking at it in this format. So it reminded me a little bit of something called the Butler-Volmer, but I realized I'm just being a bit daft, and actually then I'm realizing, okay, it is like the Butler-Volmer, because you're talking about a region where you're close to kind of equilibrium. So as in fact, it's a Nernst equation. It's the Nernst equation in one of its kind of exponential format, which reminded me where the Nernst equation came from, which is the Boltzmann distribution. That last comment about the Boltzmann distribution is for mine. It's for me to kind of go back and have a bit of a refresher on all of this. But anyway, that said, one of the big differences between Agnes and ASV is the deposition potential. Whereas with ASV, you apply quite a negative potential, so you're kind of guaranteed to get all the cations reduced. That's a strong term. The cations that are near the surface, will get them reduced and onto the surface. Whereas with ASV, if they've got different complexes, for example, of lead or zinc, you may not necessarily deposit all of those complexes, because some of those complexes may be hard to reduce than other complexes. So that it's this application of potential, how relatively close to the equilibrium potential is a difference between Agnes and ASV. Another big difference is, when we're doing anodic stripping voltammetry on this particular device, if we put a sample on here, there you can see there's really no sort of stirring involved. With the Agnes, I think they say sort of that gradient comet they had. Well, they basically, I think, rotate. I will bring in the point that they do a hanging drop electrode, and they're maybe even rotating a hanging drop electrode, but they are rotating, and that means that they kind of have this. There's not a gradient of depletion as they deposit the lead or zinc, etc., down, because they're refreshing and stirring quite. A rotating disc electrode is, let's say, fairly aggressive at mixing. Just out of interest, side comment, not really linked to this necessarily, but whereas if you want to make a low-cost rotating disc electrode system, you can just have your electrode essentially in a beaker, and you can actually just be stirring by a magnetic stirrer. I know it's stating the obvious, but I think sometimes people don't realize, and they kind of think that in order to kind of have forced convection at their electrode, then they must use a rotating disc electrode. Well, you can flow, you can stir, etc. So just FYI. Now they are using hanging drop mercury electrodes, so it's something I'm aware of. I've never done it. It's been kind of slowly phased out, because whenever you say the word mercury, you already know this is a sort of toxic setup. It's a toxic metal. But you have a mercury reservoir. You make an electrical connection with that mercury in that reservoir, and then you have this kind of hanging drop. I mean, I can see why it's got some benefits. It's got some benefits that could probably make some quite nice electrochemistry, because you've got a nice clean surface, a good control on that reproducibility of that surface, a good control on the size of that drop, etc. So I can see the advantages of giving you beautiful reproducible electrochemistry, and then you could have it in a sort of beaker like this, and then you have to have an external reference and counter. I'm going to make some points in a bit that say, we can learn something from Agnes, but I do think it needs to be applied now in this modern era to electrodes more like this, because then we can actually get it out of the lab. But I will make some points about that shortly. Just a side note on mercury. I just want to make sure that nobody thinks that I'm promoting their use of mercury. United States, mercury is classified as a hazardous material. So, really be careful if you shouldn't be using it, is the quick answer. In Europe, we are encouraged to find alternatives to mercury, and there are some conventions out there, and international conventions as well, that kind of really trying to phase out the use of mercury. So if I'm talking about hang and drop mercury electrodes, I'm absolutely not encouraging anyone who's watching this video to start doing this kind of work. It's I think actually there are other ways of detecting heavy metal. You can use nice inert materials like this, and you can make low cost, easy to use assays. So be careful with mercury, and I'm in no way endorsing the use of mercury. I would not want that. I also think that there's a direction in analytical sciences, and this direction in analytical sciences is really following the direction in the medical industry. Once upon a time in the medical industry, and currently to some degree, definitely in the water industry, you have centralized testing, a centralized testing lab where somebody will go out, collect a sample, send the sample back to the lab. The lab, after some time, will process that sample. A report will go out, and somebody will, may take some action and send some sort of action back to the field. Now, this problem with the whole thing here is it actually takes time. So collecting the sample to the lab, sample's analysed, sample gets maybe reported to somebody else, and then some action is taken. That all takes time. Time actually means money. But it also means that the ability to take some positive action when something's actually going wrong is, by the time you find out, it's all a bit too late. I mean, this is happening a lot in the water industry. We are in the UK, we're discovering that, there's been sewage leaking for several days, etc., or even weeks. But it's all a bit late. It happened, October, November kind of thing. So immediate. So I mean, of ZP, we are ISO 13485. So we do a lot of contract development, contract manufacturing in the medical industry. And so what we're really part of is actually saying, okay, there is somebody who cares, who's receiving that report, who actually wants that result. So actually putting the technologies more in their hands and actually taking out this complex workflow and saying, okay, here's at least a small, easy to use device. Put your sensor in, put your sample on the device, use your smartphone to run that assay and actually get the result back on your phone. That's what we're enabling. And it's I think that's definitely something, people are talking about point of care diagnostics in the medical field. And I think, in the water industry, you could kind of call this point of need testing. And then you put the sample on there and we give a result within a few minutes actually on the phone. That's what we're doing at ZP. Now, I think this is relevant to Agnes as well, because I think with Agnes, there is things to be learned from the Agnes technology, but I think it does need to become more of a point of need scaled, in order to have, let's say, more impact or have a greater impact. I did look at Agnes versus ASV, and I did Agnes and ASV. I didn't want to put versus, because the principles are slightly different. One of them is equilibrium based. That's the Agnes. ASV is very dynamic in terms of it's all diffusion control. We put enough potential on there that there's not really an equilibrium as such. It's just as soon as that metal hits that electrode, we're going to reduce it. So the focus of it really is on the total analyte concentration rather than necessarily understanding speciation. So we're not sensitive to the speciation. If lead or zinc are complexed in different ways, then we are kind of going to lose that detail. The ASV system that we have is actually, we do get the result in some minutes, but as I say, it's not sensitive to speciation and things like bioavailability. We're just going to tell you the total amount of lead actually in that sample. So if I was sort of thinking about Agnes now and how I would apply it in 2025, I think it does need to come onto these kind of electrodes. That means it is moving away from the mercury, and it's possibly moving away from the hydrodynamic control as well. But I think we can learn something from the way that they are able to do that speciation by not necessarily just applying a gross potential like we do in ASV and anodic stripping voltammetry, but actually applying a more subtle potential. And so we can actually learn something from that. The only reason we're getting away with this, the reason that we're able to do a kind of a system where we have electrodes like this, and we can put samples on them and we can get a result, is actually the reproducibility of the electrodes themselves. There's a problem with screen printed electrodes, and actually that's reproducibility. So because we come from the medical industry, that's something we've really been working on at ZP, and I think we're the only people who are. What makes Zimmer and Peacock very different is, I'm sitting here in front of one of our potentiostats. The biggest user of these potentiostats is actually Zimmer and Peacock. We're by far the biggest users of them. We actually use them in our own product. So this is a potentiostat that I can sell to, a university in Spain, for example. But I also use it as an instrument. I use it for actually testing the capsaicin in chili with my clients. I also use it for testing lead in water with my clients. And by the way, it's a potentiostat as well. And in developing these lead assays or these capsaicin assays, we're also supplying screen printed electrodes. So we've got a very different kind of business, because we really care about the quality of these screen printed electrodes, because if they're not good, it's not going to allow us to be able to run all of our products either. So it's a little bit different the way ZP operates. But anyway, you have to put a lot of effort into the screen printed electrodes. What's held up sometimes the use of screen printed electrodes in water testing is actually reproducibility of electrodes. But at ZP, every time we manufacture, in fact, I'll grab some here. Every time we manufacture, we put a really big effort into making sure that all these individual sensors are actually reproducible. So that's something we do a lot of testing. I think something you might notice at ZP, especially if I do a quick demonstration, actually, I didn't, is we've got a very strong data analysis tool called Julie, where we crunch most of our data. So we will go through all our production, making sure that our production of screen printed electrodes is reproducible, because if we don't get reproducibility on the screen printed electrodes, we're certainly not going to get reproducibility on these final assays. And I will put a link to some of the technologies I've shown here. Actually, I'm going to do a quick demonstration now, just to kind of give you a sense of the workflow. So what I'm going to do, I'm in the lead assay at the moment, but I'm just going to change to an assay that is not toxic. I'll just go to one, depends on your liking for chili sauces or not, but it does show the workflow. So I've just changed from lead to chili. I did it by just scanning a QR code. We live in a wonderful era where actually these smartphones are fantastic. They've got cameras that work really well. I scanned the QR code. Once upon a time, you'd have to have a conversation with somebody what a QR code was, but in fact, you don't need to have that conversation anymore. I must admit, I've been following QR codes for a good 15 years. What I'm now going to do is show you the next example of, in fact, this is a good example of electrochemistry as well. See this sample? Pretty dirty, pretty grimy actually. But I'm going to put it onto this sensor, which I will do now. 50 microliters is all it requires. That's why I think Agnes can come onto a platform like this as well, because then it will actually, only needs 50 microliters in fact to run that sample. I'm just going to give this sample a name. So this is so I can find this sample later on. So I'm going to save it in a folder called demo. I'll just call this tab 99. Continue, start. And it's basically running. So I can see the raw data kind of streaming to my phone now. You'll see what happens with that shortly. But just to demonstrate the kind of workflow and a kind of thing that I can imagine. Now, we're using ASV, anodic stripping voltammetry, quite happily to measure lead. But I think, there's some merits, let's say, to the Agnes technique. And if it can come onto a platform like this, then actually it can have, let's say, more, impact as well. So I have a result on my phone. So that's the nice thing is, see, I didn't leave people hanging with my voltammetry. I actually gave them a, let's say, real technique. But I also want to, real technique, a real number. But I want to just show you that, in fact, let me just change the screens here. So this is a database called Julie. This is something that people can create accounts with it. But it exists in the cloud. It's the only data management system for electrochemical data that's commercially available. It's 100% developed in-house at ZP. I can see my device. I can see my my data shortly, and I'll be able to interrogate. So there's my data, tab 99. I'll just click into that. and I can see my raw signal. So I can see the name, the date, the time, who did it. Especially, if you're working with kind of citizen science programs and stuff where traceability, etc. It's quite hard. We can also open up. We don't need to have geo positioning for measuring this particular sample, but we can also open up that we can actually grab the GPS of the phone as well that did the device. But in this particular case, see the way we've got the raw signal here? We've got all the raw signal. So if somebody's kind of arguing with me, is it lead, is it cadmium, is it zinc, is it copper, is it just flatlined, etc. I can really go in there and see what's going on. And there's a whole bunch of tools in here that I can really dig in and find out a lot. This is not all closed up, by the way. Real people can go in. Non-electric chemists can go in here as well and have a little play as well. But that's just a quick demonstration. So I kind of thinking to myself a little bit that agonists can teach heavy metal, the people interested in heavy metal detection something, but I think it needs to essentially come out of the lab and actually go into the hands of essentially the real users. And I think the platform I'm demonstrating here, the Sense It All, is definitely one way, let's say, of doing that. Okay, right. Question number 2 is about transdermal biosensors. I'm absolutely amazed that we do get asked this, but I'll answer it now. Does Zimmer & Peacock work on continuous sensors, continuous electrochemical sensors? Let's have a little look. There we are. There's a willing volunteer. This is a very different form factor from the sensors I've been showing so far on lead. But just know that is also, though it looks very different, is actually a continuous sensor. But here, or rather, this is a continuous sensor and it's an electrochemical one. But here we're monitoring materials just underneath the surface of the skin, and we're actually correlating it with by doing blood tests at the same time as well. So be in no doubt that Zimmer & Peacock has very good technology for continuous measurement. Most of the continuous measurement that's going on in the world at the moment is, or rather we're developing, is around environmental and let's say agriculture, so continuous nitrate monitoring, for example, and continuous monitoring of things like glucose, lactate, potassium, etc. So we are busy working on that kind of, I want to say stuff. In fact, I've got this in the slightly wrong order here. So I just want to get onto my question number 3, in fact. My question number 3 was, at ZP, do we do embedded sensors on flexible electronics? So the quick answer is we do have images in the public domain where we do have our sensors on flexible electronics. I mean, this flexible electronics work that I'm showing here, we were actually doing this 10 years ago. So you can absolutely do things like potentiostats on flexible electronics, and ZP definitely doing that 10 years ago. The miniaturization of circuits. Now these circuits, this is not particularly miniaturized. The person asking this question really needs miniaturization, but you should really be able to get. I don't want to be too hyperbole on this, but you should be able to shrink the electronics for an electrochemical biosensor down to the size of down to a sort of grain of rice type size. We haven't done it, and it'll take quite a lot of work, but you should really be able to get down to that kind of size. We are doing embedded sensors, so we are linked to human health, and this is important. That when we do this kind of work with animals, what we're really trying to do is actually, I mean, there's a group of diabetics out there, type 1 diabetic children, and actually they're possibly most at risk of hypoglycemia in the night. And if a diabetic gets hypoglycemia, they can unfortunately go into a coma, and if it's not caught, they can actually die. So we are working on embedded sensors, and we are literally doing this at the moment. The thing that this person also requires is a closed loop where they have a sensor linked to the dosing of, let's say, a drug. Now that is something that we are also working on, but in a very different space, let's say, different analyte, different space, different area. So we do understand it and we are working on it, but we're not doing it at this moment where we're doing it in a very obvious kind of application in sort of diabetes, let's say. So it's the closed loop part that we're essentially weaker on. Now I do say thank you here, but I'll just summarize the questions. So this week we have done quite a deep dive on ASV, anodic stripping voltammetry, for the detection of lead. It was just a bit of my own interest that I actually went into this technique that has been around, as I say, for coming up to now. If we're going into 2025, you could argue it's been around almost 26 years at this point. Agnes, which is this kind of, they're doing depositions of lead, but more at the equilibrium potential of lead deposition, rather than ASV, which is much more kind of, we're working far away from the lead standard potential, and actually we're under kind of diffusion control. So we did talk about Agnes and ASV. We absolutely at Zimmer Peacock are doing continuous measurement systems. I showed a kind of a very unusual setup, but actually it's not unusual. For us, it's measuring materials in an interstitial fluid. And then just finally, I was just wanting to show that we can work on flexible electronics. We can get quite miniature. We haven't done closed, we are doing closed loop systems rather, but I don't have anything in the public domain on that. Okay, look, I appreciate anyone who's watched and liked this video. If you have any questions, many of the questions we answer, they're not from clients, they're just from people who are sometimes students, etc. So if you've got any questions, don't hesitate to reach out to us. Okay, thanks very much.